example 3, when we're integrating this function, we first of all look at it, and it's definitely not a standard integral. So we need to try to see if there's a substitution. And for substitution, we look into the inside function. In this case, there's only one embedded function, which is cos. And we're going to let u equal cosine x, and then the derivative, we want that to account for the outside function. So du is equal to sine x dx. We can see that is represented by the remaining outside portion. So we can do a nice clean substitution here. So this then becomes the integral from x equals 0 to x equals pi over 4. And again, we need to write that in because we're going to change our variable from an x variable into a u variable. So we're going to let u e to the power u, and then we're going to replace the sine x dx with a du. So at this point, this is a fairly easy integral to undo. We have e to the u, and the bounds are going to be from x equals 0 to x equals pi over 4. And until we change that back to x, in terms of x, we need to keep that in there. So we're going to do that here. So instead of using u, we're going to return that back into cos x. And now our bounds can be in terms of x, which is 0 to pi over 4. So when we plug this in, e to the cos pi over 4, well, cosine of pi over 4 is going to be 1 over root 2, minus cosine of 0 is going to be 1, or e to the 1. So this represents the area underneath that curve, the original curve of sine x e to the cos x from 0 to pi over 4. For this next one, again, this is not a standard integral. We can't split this up because the denominator is a binomial. So we need to look for a substitution. And in this case, we're going to let the inside be the denominator. So we're going to let u equal x squared minus 1. The du is in the derivative, 2x times dx. And we can see that the derivative does show up as the remaining part of that expression. So this lends itself to substitution. So we're going to integrate from x equals 2 to x equals 4. And this becomes 1 over u. And then the du is going to replace the 2x dx. So that I just get du like that. Integrating, this becomes log of u. And the bounds are going to still be in terms of x equals 2 to x equals 4. And we're going to plug the u back in. The u was 1 minus x squared minus 1. And the bounds being from now, I don't need to write the x in anymore because my variable is now x. When I plug this in, I get log of 16 minus 1, which is 13, minus, when I substitute in the 2, it becomes 4 minus 1, which is 3. So this simplifies to log of 13 over 3. For this one here, the embedded function that we can try using is, well, the log x, if I differentiate log x, the derivative is going to be x dx. So that's what I'm going to choose here. So I'm going to let u equal log x. The du can then account for the denominator x and the dx. So there's my outside du part. Again, I can then put this into a u integral. So because it's a u integral, I need to make this x equals 1 to x equals 10. And this becomes u in the numerator times a du. Okay, well, this just is a power rule. So when I integrate this, I'm going to end up with u squared over 2. My bounds are in terms of x's, and I still have a u expression, so I need to put x equals 1 to 10. I'm going to replace the u with a log x, so it becomes log x squared divided by 2, and now the bounds can be in terms of x equals 1, so I don't need to write the x equals anymore. I can just write this as 1 to 10. Okay, so then plugging this in, I'm going to end up with log of 10 squared divided by 2 minus log of 1 squared. Well, log 1 is 0, so this just becomes log 10. This is all squared over 2. Okay, please make sure you don't apply the square into the log, because that is on the outside of the log, is not on the argument of the log, which is 10. Okay, so that does not apply here. We need to leave our final answer like this. And again, this is area. So we're talking about some area units squared.